Every smartphone and AI network you use today relies on one relentless physical reality, the continuous shrinking of the semiconductor. Yet the corporate pioneers who actually invented the consumer electronics industry, massive giants like RCA and Philips, are largely gone or shadows of their former selves. In this sector, getting there first offers no long-term protection. Success requires a company to continuously force the physical technology to become smaller and more efficient. Survival in the electronic century meant looking past early victories to master the art of continuous, compounding learning. This is a glass vacuum tube. It was the foundational component of first-generation electronics, designed to amplify electrical signals to make radio and early television broadcasts possible. But these tubes had severe physical limitations. They generated extreme heat, consumed massive amounts of electricity, and relied on fragile glass enclosures. Faced with these physical bottlenecks, RCA shifted its strategy. Instead of engineering a better component, they diversified into a conglomerate, pouring resources into unrelated businesses like Hertz rent-a-cars and frozen food companies. As RCA's focus drifted away from technical engineering, their leadership in electronics evaporated, leaving their home market vulnerable to a new generation of components. The engineering solution was the transistor. This is a replica of the first point-contact transistor. It was a solid-state device, meaning it had no fragile glass, it ran cold, and it occupied a fraction of the space. Japanese manufacturers like Sony and Matsushita committed fully to this new technology. They used a relentless process of continuous learning, iterating on the transistor's design to build efficient, consumer-friendly applications. The result of that applied learning was a total market shift. Sony commercialized compact, portable electronics that displaced the market share of older rivals. Japan's market gains showed that a company's ability to learn and iterate is what determines long-term survival in high-tech industries. As engineers tried to build more complex computers, they hit a new physical wall. It became practically impossible to manually wire millions of individual, discrete transistors together. Robert Noyce's integrated circuit breakthrough was to oxidize a semiconductor's surface, then etch away portions to reveal isolated N-type and P-type regions. To connect them safely, he developed surface metallization, depositing a metal layer straight across the insulator to bridge active regions. IBM leveraged this integrated technology to build the System/360, allowing them to dominate the mainframe era. But as this NASA computer room shows, these systems still required a massive physical footprint. Eventually, the integrated circuit evolved into the microprocessor, shrinking the computer from a room down to a desk. To capture this new market quickly, IBM built its personal computer using an open system architecture. But by making the PC an open system, IBM lost control of the core architecture. Suppliers like Intel and Microsoft captured the value of that massive scale and became the new industry leaders. We have gone from computers that fill entire rooms to packing billions of transistors onto a single sliver of silicon. These two microprocessors, photographed next to a metric ruler, show the microscopic scale of modern computing power. This progression toward the microscopic was forced into existence by firms competing to outpace each other's technical capabilities. Economist William Lazonick explains this through the difference between an optimizing enterprise and an innovative enterprise. The history of the electronic century suggests that once a company prioritizes protecting past victories over acquiring new technical skills, its eventual collapse is only a matter of time.